going to be. Why do I put password every time? Yeah, is my screen visible? Yeah, okay. Yeah. So essentially, the plan for today is going to be uh, do some get to a level at which in the next session we can go through some quite advanced topics in group theory, which I think you might be like, okay, are these topics like very new or something? Well, some of these might be, but many of these actually has been only discovered for like 1 century ago or something. So these topics are quite new, and much of the major application of it happens to be in the 20th century only. If you have heard of an algebraic geometrist, what was it? Alexander Grothendieck. Yeah, looks like a Chad, by the way. You should search his name up once. So, other than being a Chad, the guy is actually one of the greatest people in math known, because he is known to be one of the fathers of bringing in few topic, basically producing most of the works in algebraic geometry as a whole. So what do I mean by that is, because of the stuff we are going to look at the end of today, or maybe in the beginning of the next session. So essentially this will tie up to many things, like how groups are generated, what exactly do we mean by generators in general, uh, when can we talk about there being no subgroup that is bigger than a subgroup given to us. So these questions might seem trivial at first, because you're like, okay, if I have let's say a subgroup given, the mere question of if there is a bigger group than that, that question is in fact easier to answer, because a group is given to you, a subgroup is given to you. But the question of how many such maximal, so essentially, if there exists no bigger subgroup, the given subgroup is called maximal subgroup. So the question of how many maximal subgroups being there, or merely given the cardinality of a group, and when I say cardinality now, of course, I mean finite groups. So if given a cardinality of a group, when can we say, or what can we say about the number of maximal subgroups of such a group? So these questions are very much important, because it baffled many of the mathematicians for centuries. And if you remember, or whoever attended the last session, if you remember, I had told about this one program that has been going on. So I forgot the program's name. I had mentioned the program's name, but nonetheless, the point of the program was to essentially classify all the groups there are. Not all, but at least most, in the sense, at least finite groups. Yeah. So that program is still going on, of course, but major part of it actually comes from classifying the maximal subgroups of a given group. So essentially, today our aim would be to get into defining what maximal subgroups are, and how can we actually study them. And they are studied through, ironically, rather studied through the action of a group onto themselves. Now, when I say action, if you remember from the first session, I had told something about how we defined a group. So there was a set given, and we were like, okay, we want to see functions, essentially an action. So if you have, let's say, instead of a set, we had said a shape. So if you have a shape like a triangle, we were like, okay, we want a set of actions that preserve some kind of desired property. In our case, it was looking the same. So with similar ideology, you can actually define action of a group onto any other thing, and then study what all things are preserved. And these are characterized by other things that we define called stabilizers and orbit. And there's a very fundamental theorem called orbit stabilizer theorem, which, believe me, even though it sounds very dangerous, it's the proof is essentially one line if you know how the definition works. If the definition is clear to you, the proof is essentially one line. So till that part, today's session will be very easy. In the beginning, we missed isomorphism theorems last time, so I will go through that for today. And essentially, after our whole, so these are our agendas. So first is going to be, I'll rather put it in non-permanent ink. So first would be isomorphism theorems. Second would be followed. So the second would be defining what group actions are. Okay. The third would be the orbit stabilizer theorem. Fourth would be Sylow's theorem. Now, of course, whoever is familiar with Sylow's theorem, they will be like, okay, how are you exactly planning to do the whole theorem today? And I don't actually. So the thing is, the whole Sylow's theorem, along with its proof and everything, is quite beyond the scope of any of these sessions, because it will at least require like 3 classes. So that is why we are not exactly gonna prove Sylow's theorem, but of course we are gonna see Sylow's theorem and how exactly it's relevant. So those are the 4 main agendas. The next would be actually to define a few groups, or rather, I will do it in between. That's why I wanted to put it down separately. Permutation groups. These are kind of like a very fun group to think about. I was thinking of not introducing this in this whole thing because I was like, okay, it might take up time, but I was like, okay, this is a nice structure you should be familiar with at least. So permutation groups, and how they are actually very quite more fundamental than you think. So how they are more fundamental. So even though permutation groups might seem like, okay, these are essentially, by the way, set of permutations. How they form a group we'll see, but permutation groups are essentially a group of permutations. And then we have something called, that I was talking about, the most fundamental thing that is applied in many other parts of algebra in general and even topology, free groups. Again, for free groups, I'm not gonna talk about the fundamental structure and everything, because I will mention those fundamental structures in the next session. So it will be going through how free groups are more. The name suggests they are free, and they are free because of something called universal property. And universal property in general means, let's suppose. So I'll give you an example. If I tell you every bit of characteristic of me, will you be able to identify me? This is the problem of group theory. And group theory says I might not be able to identify you as the same person per se. Let's say it might not identify me as, let's say, Vivek TA, but it will identify me to the extent that if any other person is given to me, if any other person is given to them, they can at least tell if I am an identical twin of them or not. And that is what it means. So that is what uniqueness in group theory means. You given properties, you might not be able to, let's say, you probably won't be able to say what exactly the fundamental things in the group are. Like you can't exactly tell them by name, let's say, but you can always comment about their properties, about how they act on other stuff. That is what group actions are, and what exactly the structure is. That's all you can comment about. So the identity of a group is represented by its structure and not its fundamental elements. So that is what isomorphism means. So when we say group G is isomorphic to H, it is essentially to say G is the same as H up to the structure. So that is why in most of algebraic topology, geometry, or anything algebra in general, you will see people say that, oh, so example in, let's say, topology, people say, I mean, of course I don't want to mention how they are relevant, but point is, people say that, okay, a cup is topologically the same as a donut, a cup with a handle, of course. So how they are equivalent is not important. The important part is to say in topology, we consider both of them the same because they behave in some ways similarly. So topologically, we say they are the same, and that's the same in group theory. In a larger class of subject or a larger subject called category theory, there's a more general definition of what an isomorphism is. And there we say two things are isomorphic if they are categorically isomorphic, in the sense if they preserve the structures given on their categories. Now you don't have to go through what exactly I said right now, but in essence, what I'm saying is in math, if people say two things are the same, they might not mean they are same up to its characteristics, but up to the structure. Now, you might think of characteristic as the structure itself, which would imply you are very much mature enough to do a more, let's say, advanced math. But point is that's what I wanted to talk about, because at some point, if I say a group is the same as this, you might question, okay, didn't we define it a different way or something? So I'm like, yeah, it might be different up to elements, but structurally they are the same. Anyways, now we'll start the session. Officially, because now it's 5:18. So yeah, point is, first we'll go through the one of the most fundamental theorems in group theory, the isomorphism theorems. And for that we need to think about what the kernel, how the kernel behaves. So how did we define kernel? Given a homomorphism of group G to H, we defined kernel of phi as being equal to the set of all elements in G such that phi of G equals the identity element in H. This is essentially how we define the kernel. So what we now want to see is how exactly the kernel behaves. So if you took the conjugation map on the kernel, so if you remember what the conjugation map was, the G conjugation map, if I put the conjugation map as CG, G2, G. The G conjugation map was G is a given element in G, by the way. So this is fixed. So G, I should write G1. So G1, G1 inverse. My bad. I meant this is the map. So G goes to G1, G1 inverse. This is what the conjugation map was. So now we want to essentially see how our kernel behaves under this conjugation map. So if you take any element, let's say H belonging to the kernel, and you put G1, H, G1 inverse, and take phi of that, can anyone tell me what this is going to be? Someone? Shravya, Shruti, someone?
It'll just be phi of h, right?
Yeah, exactly. But what is phi of h? Remember where h is from and look at the definition.
Will it be the
You get
identity?
it? Exactly. It will be the identity. So essentially, if you take an element from the kernel and you put the conjugation map of that, it's going to give you the identity itself. So whatever you put the conjugation map to be, the next element, in fact, is going to belong to the kernel itself. So G1H G1 inverse belongs to kernel of phi because, well, this element, when phi is applied on it, it gives you this identity element, which by definition implies it belongs to the kernel. So the point being, it follows this kind of a structure that if you take any element G1 and you take its right coset, I think I defined it as left coset. One of these cosets, right or left coset, I forgot which one I defined this as. This itself is a set, and then you take the the corresponding other coset from the other side. This becomes a subset of the kernel of phi. Is there a doubt as to how this comes? If you think this part was confusing, please speak up. Because if this part is fine, then we can essentially the rest of the things is going to be very much easy. You understand this part?
What exactly is the kernel, though?
Yeah. So that's what I'm saying. Just if you have any doubts at any point, be free to speak up. So the kernel is essentially defined as the set of all elements such that the image is the identity. So think of identity as a zero. So set of all elements such that it's mapped to zero.
Okay. Um,
Yeah. So we prove that if under conjugation, the under the conjugation map, the if you do conjugation of, let's say, h of an element in kernel, it again gives you an element in the kernel because this itself is an element in G, right? So if this is an element in G, and when phi is applied on it, it gives you identity. That
yeah.
implies this also belongs to the kernel.
Yeah.
So this set is a subset of the kernel,
Yeah.
right?
Yes.
Yeah. But essentially now this part I think it is easy. So you can take it as an exercise, but you can prove this other subset relation as well. This is as easy as proving that this map G1 dot G1 essentially put some other element in this. This map is an isomorphism. If you prove that this map is an isomorphism, you are essentially done. So this part is very much easy to prove. So essentially, what I get is a relation G1 kernel of phi on G1 inverse is the same as kernel of phi. But we remember we had proved that kernel phi is in fact a subgroup. So any kind of subgroup of G that follows this kind of a relation, G inverse equal to N for all G belonging to G. Remember this for all is necessary. So for all elements, if the conjugation map of this subgroup gives you the same subgroup, then the subgroup is said to be normal subgroup. Do you understand what a normal subgroup is?
No.
So essentially, you just have to look at this property. Do not think about what exactly or how exactly you might interpret it in the sense what might be its significance, because we'll come to it in a minute. But
Won't
the
all the
point
subgroup
is,
be the normal subgroup?
okay. So now you have to see if all subgroups are normal subgroup or not. So for that, is it necessary that I'll show you an example. If you took, let's say, D3, which was set of all elements such that or set of all actions on a triangle, right? The elements of these were, you had your what is this thing called, the rotation. So you had identity element first doing nothing, then you had rotation once by 120 degree, rotation twice by 120 degree, thrice will again be identity, so you don't do anything. Then you had the mirror across one of the axes, and then you had all the combinations that are possible. M rho and uh, rho square M, I think. Yeah. No, M rho square. My bad. Rho square M is going to be the same as M rho. M rho square. So these are all the elements. Now, if I take a subgroup, uh, if I take a subgroup of this, let's say just E and M. This is a subgroup. Can you see that?
Yes.
Because M square is just going to be E. So this is a subgroup. Now, if I apply rho on it, so rho M rho inverse, rho inverse is going to be equal to well, try to take it as an exercise to prove, but this is essentially going to be the same as first taking rho on both sides. So let's suppose it is equal to M and then rho and then square. Yeah, I think this is it. So this is going to be equal to M rho square. Point is, how is it equal to? You take it as an exercise. I am not sure if this relation is correct. It might be equal to M rho as well. But if you take M rho and apply rho inverse on both sides, you get rho M equal to M, which is not correct. So that's it. This is correct. Yeah. This relation is correct. So essentially what I'm saying is, try to take it as an exercise and prove how this is true. But point is, if you take conjugation map of this rho n rho inverse, this is going to give you first with E you do, and first with E if you do, rho E is going to be just rho, so it's just going to get E. And if you put M, it's going to give rho M rho inverse, which is not equal to M. So you see, it's not a subset, so it can't be equal for sure.
Yeah.
So essentially what we want is a subgroup such that this property is preserved. And we just saw that this is not always preserved. So that is why these kind of subgroups are in fact not normal subgroups, even though it is a special property and you should say they are not normal, like subnormal or something, but turns out these are what are called normal subgroups. And the reason as to why these are called normal subgroups is because now this is a theorem that you can prove that given a normal subgroup, yeah, if a subgroup is normal, you denote it like this with a triangle instead of just this sign. So if n is normal to G, there exists a map phi from G to some group H. You can prove that you can take H to be G itself, some H, such that kernel of phi equals n. This is a theorem that I will not prove because, well, by the way, this is not a very hard theorem to prove as well. But it will just require you to know the first isomorphism theorem. That is why I'm not going to prove it, because you can directly prove it to the first isomorphism theorem. So, anyways, these are what normal subgroups are. So, are you clear with what normal subgroups are, definitionally at least?
Yes.
Yeah. So now we can move on to then the first isomorphism theorem. The first isomorphism theorem essentially says if phi from G to H is a group homomorphism, then that's it. This is all that we require. Then, first part of the theorem, kernel of phi is normal to G, which we proved. So we have proved this part. The second part is G mod kernel phi. New notation which I will tell what exactly it is, but bear with me for a second, is isomorphic to the image, which we also had proved to be a subgroup of H. So whatever this thing is, that is merely just defined by the group given and the kernel, we can exactly predict what the image is going to be, at least how the image is going to behave. Because as I said, an isomorphism tells not uniquely what the element is going to be, but characterize what an element is going to be. So in group theoretic language, we can exactly predict what the image is going to be. But first of all, we have to define what this is. And this is what is called as quotient group. So remember we had defined what are equivalence classes. So similarly we are going to do here as well. So when I say GH, this symbol is obvious, right? It's essentially the coset given a set G, given a subset H. So elements of G mod kernel phi essentially look like G kernel phi, such that G belongs to G. That's all. So G mod kernel phi, it's essentially the set of all cosets of G with respect to the given set, which in this case happens to be the kernel. Do you understand?
I'm still slightly confused.
Yeah, so essentially, you remember what a coset is, right? So this notation is clear.
Uh,
Just this part.
yeah, I
So
actually
this
kind of
itself is,
forgot.
huh?
Uh, Actually, I forgot what a corset is. I'm so sorry.
Yeah, it's fine. It's fine. Don't worry. If you at any point, if you do not remember what a definition is, believe me, I forget definitions as much as any other person as well. So just ask what the definition is if you are not clear at a point. So this is essentially G. It itself is a set, by the way. So a coset is a set itself. This is essentially G operated on H such that H belongs to kernel phi. So you treat each of these guys as one element.
Okay.
So this is a coset. This is how you define a coset. And then you treat each of those sets as one element. So essentially, this relation that if A is related to B, if A equals BH, for A belongs to BH for H subgroup of G. This defined the equivalence relation. This I don't know if you remember, but if you don't worry. I think the coordinators will probably share notes today, so you will be able to see the notes for the first session in which I told about how this defined an equivalence relation. But the point being, this defines an equivalence relation. Similarly, in our case, this is well defined because we have an equivalence relation. But now the point being, why exactly we needed the normal part of this whole thing, right? The normal part is necessary because we don't know if this is a group. Remember, I said that this is an isomorphism. But this being an isomorphism implies this is somehow a group. So we have to define how this these elements can make up a group structure. So in a very what is it called, easy manner, if you had to define it, you can essentially see, if you apply, let's say, G1 kernel phi to some element G2 kernel phi, you have to define this operation. This cannot be inherited from our group because now it's a different group. The elements are not one element but the sets themselves. This I will define as, first of all, somehow bring this G2 to this other side. So I will define it as G1, G2, kernel phi. That's all. This is how I define the operation in this group. Do you understand this one?
Yeah.
So essentially, given this operation, now of course I am skipping one point here as to how this operation will be well defined, but think of it as the reason as to why we define this normal subgroup part. Where is it? Yeah, this one. The normal subgroup part is necessary for this because if we take this one, because not all definitions are well defined, right? If I had a random object here and I applied these two, let's say if I took a different element, it might not give me the same value. Essentially, I want to define this as a function. And as we know, a function can't take, let's say, two outputs as value, right? One element gives you one value. One element can't give you two values. So that is why we want to see if this thing is well defined. In the sense, we want to see if this is a function or not. So how this is well defined is because if I put G1 here and I take G2, G2 inverse, this part is fine because it's just E. And this is just kernel phi. Then you have G2 here, and then you have kernel phi here. You see that this thing is essentially equal to kernel phi. We had proved via normality. This gives you G1, G2, kernel phi, and then kernel phi. This is essentially equal to operating elements of kernel phi with itself, which is going to give you the same set. Hence, this is well defined. Was it confusing?
No, I actually understood this.
Huh. So that is why this is well defined, because you can just take G2 inverse here, and then this part just gives you kernel phi, and kernel phi operated on itself essentially is the same as kernel phi because of normality. And this is why this is well defined, and that is why the normality part is important, because this operation that we define here will not be well defined, because this equality may not hold if it was a random group, right? This holds only if it's a normal subgroup. And because this equality holds is the reason why this operation is well defined. And hence I can say G mod kernel phi is a well defined group. This is exactly what I called a quotient group. So is it clear what a quotient group is?
Yeah.
Yeah. So given a random normal subgroup of G, I can just define G mod n, which is the set of all Gn such that G belongs to G. That's all. This is exactly how I define G mod n. Yeah, so given this, now our as simple goal is to prove that G mod kernel phi is isomorphic to the image of phi. And the proof is essentially you defining first of all a map from Gmod kernel phi to image. So a trivial map that is possible. So I'll call it capital phi. Trivial map is Gmod kernel phi to image phi. Given G kernel phi, take it to the image phi of G. First of all, see if this is well defined. The proof of seeing it is well defined is essentially take two elements such that G1 kernel phi equals G2 kernel phi. But this would imply G1 belongs to G2 kernel phi. This would imply G1 G2 inverse belongs to the kernel. This would imply phi of G1 G2 inverse is the identity. Hence, phi of G1 equals phi of G2. Was I too fast?
Once again, I just need to like go through it.
Yeah. If this transition is, if you understood this transition, then these parts are just group theory properties.
Can you just repeat it again?
This part, yeah?
Yeah.
Or the whole thing?
No, the how you went from G1 kernel phi and the next step.
Huh. So essentially, G1 kernel phi being equal to G2 kernel phi implies, because these two, as I said, are cosets, they are essentially going to give you the same set, right? And that would imply if these two are equal, this implies G1 identity. Remember, phi takes identity to identity. G1 EG belongs to G2 kernel phi as an element, because this belongs here,
Yeah.
right? But this is essentially the same as G1, and hence it belongs to G2 kernel phi. This
Yeah.
part is fine?
Mm.
Now essentially you take G2 inverse on both sides. You take G2 inverse here. So this belongs to G2 inverse G2 kernel phi. And this is essentially EG. This part is clear?
Yeah.
Yeah. So I actually made a mistake. I should have written G2 inverse here instead of G2 inverse this side. Nonetheless, it will give you the same result, even otherwise, but the point is you should be consistent with the notation. So you understood how we arrived at this part?
Yeah.
So that defines the well-definedness. So now we have to prove one-oneness. So now the subjectivity is obvious because, well, we are taking phi of g for all g, and image of phi is essentially defined as a set of all images of g possible. So the subjectivity is obvious. We need to prove the injectivity. So the injectivity is essentially let let's say phi of g1 equals phi of g2, right? So if these two are equal, this would imply phi of g2 inverse g1 equals eh. This is fine.
Yeah.
But this would imply g2 inverse g1 belongs to the kernel of phi, right?
Yeah.
And but by that definition, you arrive here. True, right?
Mm.
If you arrive here, you go back to this thing. But that would imply the two elements. What is this? This by definition is phi of an element g1 kernel phi equals phi of an element g2 kernel phi. This would imply the two elements of which I have taken the image of, they are equal, and that implies one-oneness, injectivity. Do you understand what I said?
Yeah.
So essentially, that proves one-one. So given that phi now is one-one and surjective, this proves phi is a isomorphism of groups. So G mod kernel phi is isomorphic to the image. Point being, it essentially tells you that, oh, see, if you have a group and you have a map, I can't just tell you what the image is going to be without even knowing what exactly my image is going to look like. So that is why I was saying in the beginning, remember, the image group is not important structurally. I don't need to know what this is going to be looking like. What is important is for me to know what the map and its kernel is going to be. Specifically, kernel. Forget about the map, even. I don't even care what the map is. I just need to know what the group is and the kernel is going to be. I can exactly tell you what the image is going to look like. I won't be able to tell you the whole codomain, of course, because that would be stupid. But I can exactly tell you what the image for sure is going to look like. And that is the power of this theorem. And this is, in fact, essentially the most fundamental reason to study group theory, because you essentially, in most of algebra, deal with objects that you don't know how they look like. Things like, so I'll give you an example, and this is specifically a place where you actually apply this. Think of think of the R2 plane, right? So this is R2, and think of a circle, or rather the line R1. How can you differentiate between these two? Like, how can you say they are not equal? Can you maybe think of some kind of tool to tell me if they are equal or not? You understood the question, right?
Yeah, but like, what do you mean by to like,
In a sense, you believe, right? They are not the same.
yeah,
Like the plane and the line are not the same. But can you
yeah,
tell me why they are not the same?
because it's like two dimensional, this is one dimension.
Yeah, but when you talk about dimensions, right? You see that dimension is a very abstract concept. You're like, oh, I can go into directions. But mathematically, to define a direction, you need to define things like, oh, it's a vector space and everything. So that goes into very much jargonish stuff. Geometrically speaking, can you tell me how they are different? Like, can you see geometrically? Can you tell me some kind of structure on R2 and R that you can see and you can differentiate them?
Like, after we can talk about area, maybe.
Yeah, sure. So that is one way to look at things, right? You can talk about areas, but then on R I can define an area element in some sort, essentially length. How exactly does a length differ from an area? So this kind of concept makes it very much uninterpretable, right? So I'll give you one kind of a differentiation so that you can think of maybe one more. If I puncture a hole on R2, do you see that it becomes a structure like this? So that imagine there is a hole here. I'll just draw a void here. So you see that if you put a circle, you can't squeeze in the circle to a point because this point doesn't exist.
Yeah,
But you can't do it in R. If you do the same on R, you remove this point, you get two disjoint lines.
uh,
This was connected. This is still connected, right? I can go from this point to this without any worry. There exists a path. But there is no path here
yeah,
from to go from here to here, right? So that is one way to look at this. Another way might be to think about in the same way if you took R2 and R3. Now, R1 and R2, this was simple, right? Essentially, you had to take away a point and now you can differentiate. There are other ways, by the way. One of the ways, as you talked about, is the dimension thingy. But the thing is, to get into another structure like, let's say, vector spaces and all, is it's not very much. It's kind of frowned upon because we want to give as low of a structure on a thing as much possible. We don't want to induce stuff like, okay, let's take in a product, a dot product or something like that. What we want to do is put as much low of a structure as possible on a thing. And that is why what we go next is to R2 and R3. Can you think of something here maybe? How would you differentiate R2 and R3? You think on it and answer me in 2 minutes. Until then, I'll just move my setup laptop to this side because I need charge. Yeah, do you have a way?
Like in the previous one, like we removed a point, right? Maybe we can remove like a whole line.
A whole line. Okay. So if you remove a line in R2, it makes it disjoint, yes. And in R3, it doesn't make it disjoint. Exactly. Yeah, true. You can do that. So this kind of an idea is fine. Now you have a very much geometric way of looking at this, right? Now think about a space where you don't have information about how you define a line to be. Here you have a very nice structure. You can see stuff, right? But in spaces, let's say infinite dimensional spaces, there are infinite dimensional spaces, by the way. When I say infinite dimensional, it might not be as simple as saying, okay, R infinity. That is a space you can define, of course, but there are other infinite dimensional spaces. These are called function spaces and all. Point being, they are very much worked upon, and we want to define some kind of how we can differentiate these guys. Of course they are not the same, like R2, R3, these also must be different, right? They can't all be the same. Then the whole field of functional analysis will be useless, which I work on, and I will be jobless. So the point is, there must be some sort of way to differentiate these spaces, and that's where you come to what are these things called homology groups. So these are defined as innate homology groups. And these essentially give you a a sort of way to formalize this idea of removing a point, removing a line, removing a plane, removing a circle as well in some cases. But essentially, the point being, it homology group tells you in some ways the number of quote unquote holes a stuff has. And believe me, this group is simply defined as being equal to, in some ways, the number of number of paths, n-dimensional path. When I say n-dimensional path, zero-dimensional path, or I should, zero-dimensional paths are just points. That's all. One-dimensional paths are lines. Two-dimensional paths are planes. So number of n-dimensional paths modulo. Now these form a group in some way, or rather some form of f of this thing forms a group. But for simplicity purpose, just think of as number of n-dimensional paths. Modulo number of n-dimensional paths with n plus 1 volume. So essentially, it's thinking of, let's take a triangle in R2. If you remove this point, this path, this triangle will not belong to this, because this is a one-dimensional path, but it covers no volume because the point is removed. So it can't cover a two-dimensional volume. So this path does not belong to this. But this path as a whole actually does belong to this number of n-dimensional path. So essentially, such a fundamental concept about how we can differentiate spaces like the real spaces R1, R2, R3 and all actually very much is related to stuff like these groups, and those are defined by exactly these things. Number of n-dimensional paths divided by number of n-dimensional paths with n plus 1 dimensional volume. And this is, by the way, quotient group. This forms a group as well as this also forms a group. How do they form a group? We might talk about in the next session. Not very much in detail because, believe me, the idea itself, my professor of algebraic topology, he himself said he has no idea how someone could come up with such a weird way to define stuff. It's a very artificial way of defining this, but it gives you a very fundamental quantity that relates to actual property of spaces, as simple as the things you look at, like holes. So believe me, there is no way to actually formalize what a hole is in math. Because essentially, hole is the it's a void that there is nothing to define there. That is what a hole is. But fundamentally, to define what a hole is, you need to define what outside is, right? But in math, if you have a set, your universe is that set. For you, there exists nothing outside. So that is why it's a very weird thing to realize that a whole can't be defined. So we have to go through this very convoluted ways of somehow defining a whole without defining it. So you count the number of holes without saying what holes are. So a homology group, whatever that may be, I'm not defining what it exactly is and how they are exactly counted upon, but those things tell you exactly how many holes are. If you had counted them literally, like if you had a donut or a torus with two holes like this, you can count them one, two. But topologically speaking, or group theoretically speaking as well, I could have counted them without even defining that these are holes. So these fundamental concepts could be defined using such simple basic theorem as first isomorphism theorem is one of the reasons why group theory is very much a base theorem and a base theory in mathematics. One of the reasons why it is a compulsory course. But in the course itself, I kind of feel that it is not stressed upon that how important this field actually is. Anyways, there are two other theorems, the second isomorphism theorem and the third isomorphism theorem. I would say you would take up this as a you know an exploratory thing of yourselves, because believe me, first isomorphism theorem proves second and third easily. You can prove it on your own and you will be able to see that, oh, it's very much simple as well. So look at what second and third isomorphism theorems are and prove them yourselves. It's very much easy. I would say second and third are essentially the corollaries of the first isomorphism theorem. Then there is a fourth isomorphism theorem which is actually skipped by many books. It's called the lattice isomorphism theorem, which I will not prove because it goes into what is called class bijection and all. But it's as simple as saying, given a normal subgroup of G, if A is a normal subgroup of N, this is possible if and only if G mod A is a, yeah, I think it was this only, if I'm not wrong. Oh, yeah, yeah, my bad, my bad. A is A such that it must have N is a normal subgroup of G if and only if A mod N is a normal subgroup of G mod N. That's all. So this is a bijection in the sense this is true if and only if this is true. This actually might be very much simple to see because you're like, oh wait, this is a normal subgroup implies this must hold true, right? It is essentially kind of like seeing that okay, if you have this thing, divide by n, right? It looks as simple as that. Thing is, you just need to prove it as well. It is as simple as that, but the proof is the important part. Why I went into saying that this is class isomorphism and all, class bijection and all, what you need to prove is prove that the set of all A's and the set of all A mod N's, these have a bijection. This is the part that is important. And this goes into a more general form and category thing. That is why. But nonetheless, that point is not important to go through. So this is the important part. This is called lattice isomorphism theorem because, well, it it kind of shows you that okay, if you have a normal subgroup here, you can also find a normal subgroup here. That's all. So it is kind of like a lattice point in that in some sense. Otherwise, it's not important to see. So that's all. That is what isomorphism theorems are. So now we'll go into. Oh, by the way, isomorphism theorem is clear, right? Did you have a doubt in that?
Yeah,
What?
it's clear.
Yeah. So if
Sorry,
isomorphism theorem
I
is
have a
clear,
cold,
and
so my voice is weird.
you have a what?
No, sorry, I have a cold, so my voice is kind of weird.
Can you repeat? I missed that.
I said that I have a cold, so my voice is kind of weird.
It's fine. It's fine. No, no worries. Nonetheless, you are fine though, right? If you are too much in a thing or something, it is fine. I mean, we'll probably send the notes as well. So it's not a necessity that you attend.
No, 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 like fine, like
So yeah, okay. Then. Like I don't want to be a reason for someone getting even worse afterwards. That's all. Nonetheless, if you're fine with that, we'll go to the next part. So that's all we relate to isomorphisms. The next important part is action of a group. So group action is the same as what we actually did the first time in this whole series of lectures. It is essentially defining how a group acts on something else. So essentially, kind of seeing how symmetries work. So given a group G, and let's say given a set A, we have a group G and a set A. The action, let's say a pairing dot from G cross A to A. So essentially, we want to somehow think of elements of G as a function. So remember, in the first session, we were like, oh, we wanted to think of all the functions on the triangle. So now we are, rather than taking the triangle first, we are first taking a group and bringing a triangle from somewhere else and somehow trying to operate it on this. So that's what now we are trying to do. We take G comma A, any element, and push it to some element G of A. Defining it is a different thing. So we have not defined it. So this operation is said to be a group action if it follows these properties. So the first property is identity applied on any element gives you the element itself. So the identity is kind of doing nothing. Then this is the important part. G operated on H and then operated on A is the same as G operated on H operated on A. If these two, if this is defined, this is what a group action is. So as simple as saying your function is well behaved. Applying consistent actions is the same as applying the actions one by one. That's all. This is how I define a group action. Is there a doubt?
No.
Yeah. So essentially, how now you might ask how exactly this relates to a set of let's say symmetries. For that, we so If G acts on a group A, we also denote it as like this. So this is kind of a fancy notation that many books use. I usually don't use this because I rather actually don't really deal with groups in general. Only in the background maybe sometimes. Let's say for in function analysis when I have to go through, let's say, defining maximality of subgroups and all. Only then usually I define these, but I usually don't go through this group actions much. But point is, these are necessary for defining symmetries in commutative algebra, which is not exactly my field, but I've done a bit of it in my previous years. So essentially, how do we look at symmetries? Symmetry is to say, so this is defined by two sets. One is orbit. So given an element x, so given an element x in A, the orbit of x is defined as set of all gx such that g belongs to g. So it's a set of all elements you can get when you put the functions on x. That's all. The stabilizer, on the other hand, this is how I define stabilizer of x. This is a set of all g's such that this is equal to x. Do you understand the definition?
Yes.
Yeah, what?
Yeah. So yes.
Yeah. So essentially, stabilizer is the set of all elements that fix x, fix in the sense the output is the same as x, and the orbit is the set of all elements such that you get the output. So in a sense, this is a subset of A, while this is a subset of G. And well, if you remember from the definition, you can actually just readily prove that the if G is of finite what is it called, finite cardinality, orbit of x times the stabilizer of x, at least a multiplication of their cardinalities, these two are equal for all x belonging to A. This is called the orbit stabilizer theorem. Do you understand the proof of it, or is it not clear? Because for me it wasn't at the first time, so that is why I wanted to ask.
I think I need to think about it.
Yeah, so the thing is as simple as, so look at this part. Stabilizer is a set of all elements such that it fixes x, right?
Oh,
Yeah. So if you just look at orbit, it is the set of all distinct elements you can have. So if you have set of all distinct elements,
yeah.
there will be one element which will not be distinct, and that will be x. So you are gonna take for each element the set of all elements that are not distinct. That is of that is the stabilizer, and then you multiply. I think it was unclear, but
Yeah.
as you said, point is just try to think on it a bit more, because believe me, this is a very easy concept to think about. Actually, why not just directly try to prove it? So orbit gives you set of all distinct elements, right?
Yeah.
Yeah. So now distinct elements in A, of course. Now for each element in A, so each element in orbit, you could have arrived there. So let's suppose this element A, you arrive from g of x. You could have arrived here even if you had taken, let's say, g1 g of x, if, or rather, I should say, you could have arrived here if you had taken g of g1 x, where g1 belongs to the stabilizer. Is this part clear? Because this is equal to x, right?
Yeah.
So for each A, you take all of these elements. So G1x is going to be, each of these G1s is going to give me one distinct value, which actually just gives me x, which gives me a corresponding A.
Yeah.
So you take all such that, so for one A, you have all such stabilizers contributing to A. So for each A, if you take orbit and then stabilizer multiplied. But now how do you prove that this is equal to G? It's because we were taking G times X. Each of the element that are distinct is contributed by one element in the group itself. But that one element in the group corresponds to multiple elements in the stabilizer. Now I think I am going into a very confusing language, which I shouldn't have. The point is, I think this is better if you just think on it yourself, because
I
believe
think
me,
I
the
kind
proof
of
of
got
it is what?
uh, I said I think I kind of got it like with the G of G1 of X thing.
Yeah, exactly. Because believe me, the proof is this. That's it. The proof is just one line saying that because of this, it's proved. So to get exactly what it is, you might have to sit down and look at this one line. So that's all the proof is. So
Also, is it
assuming you have
necessary
got
that
that,
all the elements in the orbit should be distinct?
so the orbit is defined as the image of all the G on X, right?
Yeah, but
And it's a set. It's going to give me a set. So
yeah,
it's just going to be distinct elements in the set, a set, right?
yeah, but then, like two of the elements can also be equal, right? Mm.
Two images might be equal,
Okay.
but as a set, they are the same, right? In the set, they will be the same element.
Yeah. Okay. Yeah.
Essentially, kind of like taking 1, 2, 3, and 4, 5, 6, and then mapping 1 and 2 to the same element.
Yeah.
So that is why in the image, of course, it will correspond to one element, 4.
Yeah. Yeah. Yeah.
So
Yeah.
they will be distinct. Yeah. So that's all. So, anyways, coming back to our this thing then. So this is how we define the orbit stabilizer theorem. That's why I said the only the name of the theorem is the scary part. The theorem itself is very much kind of like a pooky theorem. Nonetheless, we'll go to now actually seeing the important part, that is groups acting on themselves. So groups can act on themselves in very fundamental ways, acting on themselves. And when I say fundamental, they are actually very jokingly easy ways. One is multiplication, that is, just take an element G, G to G, and just apply left multiplication. So take any element H, apply GH. That's it. This is an group action because this is well defined, right? So of course I need to, if a group action is defined by cross product, right? So I need to take G cross G. So rather I can define it as dot G comma H going to GH. This is a group action because for one, identity operation is direct. The second property is just associativity in this case. GH applied on K is equal to G of HK. This is associativity, which was actually a part of the definition of a group. So hence, group acts on itself with one left multiplication. This part is fine?
Yes.
Yes, President. Yeah. And then let's but conjugate take GH and bring it to GHG inverse. This is the part where you have to take care of this property. First property is obvious as well. Put E G is going to give me GHK inverse. This is going to be will give me give me G inverse. G who clear?
It is clear.
Uh, yeah, am I audible?
Yeah, I couldn't hear you before.
Yeah. I think there was a network connection issue from my side. Is the presentation gone?
Yeah.
Just a second. Huh? Where's the presentation? Yeah, it's disconnected from my side. I should rejoin from my this part. Okay. Yeah, better. My bad. Yeah. Anyways, so if that part's clear, essentially these two are the fundamental ways that we in general in group theory really care about looking at how groups act on themselves. There are of course other ways that you can define, but th- those are like it's not more fundamental than anything. Like most of the time, whatever we care about is conjugation because normal subgroups exist, or then it is left multiplication because we can define equivalence classes and all. In other places, I have not exactly seen an experience, but sometimes you have to go through this what are called p-adics and all, where you have to define other kind of structures like okay, what happens when you take squares and all. Then there might be you take let's say higher order these things group actions, but or else in general it's not necessary. But nonetheless, what we'll go through today is a very fundamental theorem now, which will be the last part of the basic group theory that we'll see. Believe me, this part is going to be more of a fun fact than anything, because well, it's not exactly a part that I will be able to cover with its most glory, because it's a very important part and it defines much of the importance of contemporary knowledge in group theory. So it's not as if what is it called? It essentially tries to classify all the what are these things called? All the finite groups. So finite groups are characterized by their cardinality and the fundamental structure. And if you have their fundamental structure, you can talk about okay how exactly what you can explain its subgroups and what are the maximal subgroups. So first of all, I'll define what a maximal subgroup is. So n is said to be maximal subgroup of G if there exists no subgroup M, subgroup K, such that n is a subgroup of K is a group of G. That's all. So there exists no bigger subgroup. Of course, it has to be proper. It can't be improper. I'll remove the equality. So n is said to be a maximal subgroup if there exists no subgroup that is bigger than n. That's all. That's what maximal means. So essentially, Sylow's theorem says if G, if cardinality of G has, if let's say a prime number P divides cardinality of G, or was it P to the power K? Okay, if P to the power K divides cardinality of G and K is the biggest, in the sense P to the power K is the maximum it can go, P to the power K minus 1, K plus 1 does not divide G, mod G, then there exists a, there exists a unique subgroup of order P to the power K that is maximal. And this is called the Sylow P subgroup. So this is the Sylow's theorem. There are two more statements of this which are not exactly important, because I mean they are important in group theory, but they're not exactly more exciting to look at. But the point is, like example, the second statement is essentially says that if you have two Sylow subgroups, then those are conjugate of each other. In the sense, if you take conjugacy class, if you take this group action, and under this group action you take its orbit, you can prove that two Sylow P groups are the same up to conjugation. So one of the elements applied on the subgroup itself gives you the other subgroup. That's how it is connected. Was that confusing to understand?
Slightly.
Yeah. So essentially, what I'm trying to say is define what this uniqueness means. So if you have, let's say, a Sylow P group N and M, it is essentially to say there exists G such that N equals G inverse. That's all. I think this would be easier to understand. Is this fine?
Uh, yeah.
Yeah, so essentially to say they are unique up to conjugation. If N and M are the two subgroups that are of order P to the power K and are maximal, there must exist an element G in the group such that they are the same up to conjugation. This is what the Sylow's theorem says. And well, this is a very fundamental theorem because it gives you a kind of classification for many groups of finite order. It gives you classification for D3, in fact, any Dn. It classifies all Dn. It doesn't really has to classify, but you can, of course, classify all Z mod Nz. You can classify all Z mod Nzs. And then there are what are called product groups. So product groups are essentially if you have, let's say, G and H with two operations. Let's say इसका operation is given by this plus symbol. Then G cross H also forms a group, and you can define it as with. So its elements are of course G comma H, but you can define the operation to be G comma H operated on, let's say, G1 H1 operated on G2 H2 as being equal to each of this operation applied on the elements themselves. So G1 with the operation of G, comma, I should write comma, H1 with its own operation applied on itself. This is how I define a product group. Is this definition clear? Your voice did not come.
I said yes.
Yeah. So essentially, it's kind of like adding two vectors. If you have two vectors, you can add them and they add up all the entry wise. So similarly, you apply the group operations and entry wise. That's all. Now, of course, I can define infinite product as well, but that will not be important for at least some period of time in your life because, well, those things go. So infinities are very much, you know, very much difficult to deal with because at infinite limit, you can actually define product groups in two ways. One is the simpler way, but the simpler way turns out to be the most useless thing ever. And then there is a more complex way, which turns out to be the most simple stuff you could have thought about, but you did not. Like, yeah, it is something that is missed upon, and I have seen this happening with most to everyone. There are only a few people that have ever given me an idea of forming, let's say, an infinite group with, let's say, the second idea that is actually how it's defined. But yeah, the first way, it's the most naive way in the sense you take all the possible Cartesian product and say that, okay, this is my group. And but the problem is it gives you too many elements that becomes a problem, and it is in fact a very much apparent problem in most to all of stuff in mathematics actually. Even in topology we define products, so if you have two topological spaces R2 R3, let's say, you can take their product and define what is called product topology. So there also you can define it in two ways, and again this finite infinite thing comes there as well, and you are like, oh, I need to define it in two ways. So I will define a useless product, I'll call it box product, which I'll throw in the garbage, and then I'll define a very useful thing that I feel like I can apply anywhere because it has nice structure and all, and that you define as the topological product. So yeah, similarly here also you have that infinite bullshit that happens, and that is why I won't exactly be going into the infinite part of it because it's just at that point it's just jargon. So why bother with that? Point is, this is how we define groups. So this is what is called Chinese remainder theorem. Do you know what Chinese remainder theorem is? I don't think I've written Chinese correctly. Have I written Chinese correctly? I think so. Anyways, do you know what Chinese remainder theorem is?
No.
Oh, so essentially the Chinese remainder theorem says if you have if you have equations n1 is equal to a1 mod k, n2 equals a2 mod k, and dot 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 n t equals at mod k. I think there were nk of these. Then you have unique solution a1 a2 dot 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 ak. This is what the Chinese remainder theorem says. So if these are given and this is given, you can uniquely find these guys. Yeah. No need to prove this because you will probably see this in your discrete math course. So I don't need to bother to prove it here. But the point is, there is a more general version of it. Even more general version of it exists, by the way. It's called the structure theorem in ring theory. But the point is, consider Z. So this forms a group, integers obviously forms a group. But that's not the important part. The important part is, if G is a commutative group, also called an abelian group, of course. A commutative group is abelian, so the operation is commutative. Then there exists unique n1, n2, n3, dot, 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 nm, and of course here and mod of g is finite, such that g is isomorphic to z mod n1z cross z mod nmz. That's all. That's why I said this. What is it called? Sylow's theorem is actually quite fundamental because now you have a way to literally classify all abelian groups. Now, of course, I said finite here, but you know what the infinite version is? The infinite version is as simple as saying you take one more cross with z to the power m, not m, some element k. That's it. This is the more general version of that. So if you had finite, this is the theorem. If you have infinite, if you remove this condition, this part joins in. That's it. And all of this is literally because of Sylow's theorem. Of course, there are other ways to prove it as well using group action and everything, but that actually becomes a longer way. So Sylow's theorem provides you a way to literally classify all abelian groups. Give me any abelian group in the world, I'll be able to tell you how it looks like. And as I said in the beginning, in group theory, I just need to know what a group looks like. I don't care about how the element particularly what they are. I just need to think about what the structure is. This is such a fundamental theorem, and it is such a it's such a lovely theorem because I literally now know all abelian groups. You give me any abelian group, I will be able to tell you what it is. That is not the case for all groups in general, by the way. And that is where the problem comes because in general, I don't know how exactly a group, what exactly a group is isomorphic to. So when I say classification of group, now I can tell you what classification of group means. What I mean is to somehow show that given you give me any group, I will be able to tell you if it's isomorphic to some product of groups that are already known. This is what I mean. this is what the problem of group theory is. This is called the classification program. Or, oh yeah, now I remember, the Hodger classification program, which has been going on for like now 2 centuries. The problem of the program is to essentially this: give me any group, and I'll tell you what product forms the what product forms an isomorphic group to the given group. And well, of course, the problem is not solved, and well, there are many statements on this. And one such groups that we are trying to get to is the permutation group, SN, which is defined as the set of all permutations. Now, I think defining this thing here would be useless because, well, permutation groups are very much easier to learn on your own because, well, it is as simple as take the set 1 to, or rather, take a n-gon and then permute their vertices. An action on the n-gon is said to be a permutation of the vertices. That's it. So if you have two actions and you put them right after each other, it is also going to give you a permutation of vertices. So these actions form a group, and that is what Sn is defined as. And then you can define what even permutations are, odd permutations are, but odd permutations are, by the way, not no one really cares about. So the point is, this group is nice because it has order n factorial, as you might guess, because permutation implies there are only finitely many ways to permute anything. So hence you have n factorial as its order. But the important part and the interesting part is one of its subgroup, which is defined as an alternating group, which I will not define here. But to to know a property of this subgroup A5, specifically A5, it took a 134 or 174 page long paper. This is literally the biggest paper I had ever read before this. It literally took these much worth of knowledge. And this was one paper, by the way. In this one paper, they proved A5 has this one property called simplicity. So, a group that is such, like, it is such a small subgroup, and still we wanted to prove a property, which we probably could have done, by the way, by literally writing down each of this is a finite group, and how long can it be? At the max 5 factorial. And 5 factorial is what? 120. It's easier to write down 120 what are these things called? 120 elements and do element wise calculation than writing a 174-page long paper. Still, the mere thought to do it was not to specifically prove this property for A5, but rather get some theorems that actually proved much more fundamental things about the subgroups in general that are AN. And this is what the next major breakthrough in group theory was. And sadly enough, all the people who actually did this major breakthrough died before this Fields medal concept came. But believe me, this actually was a very Fields medal worthy stuff. But yeah, this is one of the problems in, by the way, contemporary group theory. But nonetheless, that is essentially the basic group theory that you will need to literally talk about stuff that are in group theory in general. If you take the course itself, you will go through whatever we have seen till now, but in more detail, of course, going through problems and all to specifically do some calculations, see more groups, see more structures that make your understanding of these concepts much more better. Of course, look at the proofs that we missed today. Just a second, my internet is kind of hopping. Yeah, back with this. So essentially, in the group theory course, you will essentially look at more detail into the topics we have already covered. But specifically, you might find the classes a bit more slower because not because you have done the basic stuff here, but because of the fact that group theory itself is going to introduce you to the way of how proofs really work in mathematics. Because I think from your batch onwards you have the intro to proof course, right?
I'm not sure.
What?
I'm not sure. I don't know.
Oh, okay, okay. So I think I'm not sure, but there was an intro to proof course, I think. But point is, I went through the course structure, but it felt like the course exactly did not point out how actually proofs work. Because for me, at least, I found the course to be much more basic than it was. It need be at least. So group theory will kind of give you a taste into how actually proofs work in general more. Sadly enough, there are some professors, of course I won't take names, but some of them are quite famous for actually ruining the course because for one, some make it too simple by not dealing with complex groups. In the sense, I'm not saying to make the class complicated using complex groups, but I'm saying to at least talk about stuff in abstract so that you can get a get a glimpse of what exactly happens when you go more abstract in other courses. So that sense of abstraction has to be there, which was missing at least in my year when the group theory course was taken. And then it will also introduce you to how to actually think of starting to prove stuff. So when you start a proof, you don't exactly get into this thinking, oh yeah, let's just go ahead with it. Most of the time, in fact, at least in contemporary math, you don't start with whatever you want to prove, but rather you start to think in the ways of what you have already. You first think of, okay, these stuff I have, let's look at its properties first. Once you're clear with those properties, once you get a hint about, oh, this seems to be closer to what I want, what the goal is. So let's move in this direction. That's how the proof works, rather than directly jumping into the goal itself. So stuff like these seem very much easy to hear, but in practice actually becomes quite harder. Uh, that's why the PhDs, MScs, and all take like years to come up with the results, of course. Point being, it's not related to the complexity of the problem, but rather how a person looks at the problem itself. So this, at least this component, this one component, we'll try to look at how it works. Just an intro to how you look at these problems, how you actually form new structures because you think they might be useful. Those things we will, that is the goal of the next session to look at not just the reason as to looking contemporary group theory because it's like fancy stuff, but more because we'll go through this one concept called free groups and the universal properties that will give you a hint into why we introduce and define new stuff and as to why introducing some things at some points actually makes things easier. Because if you think about it, proving something literally doesn't require you to define anything. A definition at most times seems to be just, to make notation simpler, or to make jargon, or to make things more jargonish. But in many cases, actually, the definition is what answers the problem as well. So the homology thing I was talking about, there is one such instance where when someone actually defines something, is when everyone actually solved a problem. And without that one definition, no one could actually uh, get a way to move ahead with the problem. That is one instance of it. So a definition is not always to jargonize stuff, but rather sometimes to literally even start a problem. That is why I wanted the last group theory part to be a bit independent of all the sessions we have taken till now, but at least the basic knowledge of it, the basic most like isomorphism theorem and the definitions of those things are important. But other than that, I don't want this specific things here. Remember what is it called? Modular arithmetic is, or remember what these specific little properties are. I don't want to go through that part, but just go through this one thinking. Oh, let's assume I have a group, and now you understand what I'm talking about. That's all. That's all the knowledge that is required, and that is why I want to make this last part into this contemporary math thingy to actually introduce you to how you look at problems and how research works in general. So yeah, I think that would conclude our today's session. If you have any doubt, you can ask right now.